Hey everybody, welcome back. I hope everyone's doing well. Today we're going to continue our discussion of circuits and we're going to discuss Ohm's law, which is a way for us to quantify and make predictions of the electrical specifications in our circuits. Last lesson we had a circuit introduction. We talked about the fact that we're going to be exploring DC circuits for this course. DC means direct current. Direct current circuits are what are in flashlights, anything with a battery, your cell phone, your calculator, those are direct current. Even cars are direct current, the electrical in the car, because there's a battery underneath the hood. Anything that charges a battery, if it has like a box in the wire, you plug it in, that box converts the AC coming out of the wall to DC in order to charge up your phones and your laptops. Okay, so today we're going to discuss Ohm's law. It's named after this guy, George Ohm. He was a German dude, and one of the things I really like about George Simon Ohm is he was actually a school teacher. He was a mathematician, he was a physicist, he was a teacher, and while he was teaching, he came up with this idea of Ohm's law, which is a really important law for analyzing electrical circuits. We're going to use Ohm's law to better understand how circuits work. All right, before we dive in and discuss Ohm's law, I just kind of want to review how we draw these electrical circuits. So let's try a question just to get started. Get our feet wet a little bit. All right. Before we really dive in and get started, I just want to let you guys know that anything you guys need, just feel free to reach out for me, whether it's physics or otherwise. I know times are kind of tough right now, and I hope how I'm structuring your physics class is working for you. If there's anything you can do different, or if you have any feedback, feel free to let me know. I'm always checking my email, and I'd love to hear from you guys. All right, so here's what we're going to do. We're going to draw a simple circuit consisting of a battery, a resistor, and we want to include devices to measure the current in the circuit and the voltage across the resistor. All right, so let's draw out our circuit schematic. We talked about schematic circuit diagrams last lesson. We use those diagrams to easily communicate what's going on inside of our circuits. So we need a simple circuit consisting of a battery. Like I talked about last lesson, I like to always start with our cell or our battery. That's the voltage source of our circuit. So if you look on your reference table, this is what a battery looks like. Grouping of cells. Like I talked about last lesson, the Regents tends to use batteries and cells interchangeably. All you have to know is that this is our voltage source. Whether it's a cell, if it's just a single cell, or a grouping of cells for a battery, it's our voltage source for our circuit. So we need a simple circuit, we need a battery, we need a resistor. And if you remember from last lesson, our resistor looks something like this. Just a jagged line. Okay? Now, recall from last lesson, is this circuit going to work right now? Well, we have our voltage source, but if you can see here, our circuit is not closed. So this circuit will not work. We need to make sure we have a closed loop of conducting wire. There we go. Now this circuit will work. But the next little section says we want to include devices to measure the current in the circuit and the voltage across the resistor. If you remember from last lesson, we need to make sure that we put these devices in the correct locations to make sure they work correctly. The device to measure current in the circuit is what we call an ammeter. So we have our voltage source, we have our resistor. This circuit will work. But if I want to know how much current is flowing in the circuit, I need to make sure I put an ammeter in series. Remember what current is. It's just checking how much charge is passing that point every second. So we need the ammeter in the path of the circuit so we can look and see how much charge is passing every second. So there's our ammeter. Now we can see how much current is flowing and we can actually see that this circuit is working. We're also going to need a device to measure voltage across the resistor. That is our voltmeter. And if you remember, voltmeters need to be connected what we call in parallel, creating a whole new path. Like I said last lesson, I like to think of voltmeters as checking the electric potential here and the electric potential here. It's got to look in both of those locations to figure out the voltage, the potential difference across the resistor. And there it is. There is our circuit schematic. Now, we said last lesson that resistors quite literally resist the flow of current. By putting a resistor in, it makes it harder for current to flow through our circuit. Now that sounds like a bad thing. It has like a negative connotation, resistor, but we need these resistors to make sure all of the components in our circuit are getting the correct electrical specifications. We don't want to fry out any of our components. Let's officially define what electrical resistance is. Resistance is the opposition to the flow of current. Okay, so now we have three electrical quantities that we're keeping track of. The voltage, what the voltage does, it creates a potential difference in our circuit, and current won't flow unless we have that potential difference. So we have the voltage to pump that current along. We have the current itself, which is literally the flow of electricity through the circuit, the flow of those charges. And we have this resistance to oppose the flow of current. Now, how do those three quantities depend on one another? You can see that they kind of have some kind of relationship to one another, right? The voltage is what allows current to flow. The resistance opposes the flow of current. We could actually put together all three of these quantities into one equation, which we call, you guessed it, Ohm's law. All right. So I'm going to, let's do this. Let's write down Ohm's law. What Ohm's law says is the resistance is equal to the voltage divided by the current. And that's it. This equation is in your reference table. You can calculate the resistance if you know the voltage across a particular device and the current flowing through it. So let's say I didn't know the resistance of this resistor, right? We can quantify how much it's resisting the flow of current and get a number to it. So if I didn't know it, but I did know the voltage across this resistor using my voltmeter, and I did know the current flowing through the circuit, we can use these two quantities to calculate our mystery resistor, how much resistance it actually has. So this is potential difference Remember, potential difference is just another word for voltage, right? Scientists like to use the word potential difference more than voltage, but we'll use them both interchangeably here. This is the potential difference, the difference of potential between these 2 points. How many volts are here? How many volts are there? Okay. That's the potential difference. As you recall, I is current. Potential difference is measured in volts. Current is measured in amps. Okay, and R is what we call the resistance. We're going to use this new equation to calculate what's going on inside of our circuits. We're going to take our qualitative understanding from last lesson and hopefully apply some more numbers to what's going on here with this equation. So we defined a new term. We know it's resistance. How do we measure it? How do we actually put a number to resistance? Well, the SI unit, the metric unit for resistance, as you can see, it is volts per amp, right? Volts over amps. We have a special name for this volts over amps, and we call it an ohm. Why do we call it that? Well, you could thank this German dude, George Ohm. So resistance is measured in ohms. You could have a 10 ohm resistor, a 20 ohm resistor. Some resistors are even measured in mega ohms, which is millions of ohms, right? And so here is the SI unit, and the symbol we use for ohms is going to be another Greek letter. Sorry about that. But ohms, the symbol we use is omega. And you can guess why we picked omega, right? Ohms, and the Greek symbol is omega. Looks like an upside down horseshoe. Okay. Another thing to keep in mind here, is this a vector or a scalar? Well, if we're quantifying the resistance of flow, there's really no direction needed there, right? This is a scalar quantity. Just how much is it going to resist the flow of current? Okay. And, just like I said before, 1 ohm is equal to 1 volt per amp. We got all kinds of names floating around when it comes to electricity, right? Volts are named after, I think his name was Alessandro Volta. Amps are named after Andre Ampere. And now we have ohms named after George Ohm. Okay. I'm going to erase this side here. But then I want to kind of talk about Ohm's law a little bit more, then we'll dive into some examples. So you got that, pause the video, write it down. Flimsy little setup here. Gotta fix it. Okay. So we said Ohm's law is R is V over I. I like to explain, so this is how it shows up in your reference table, right? But let's rearrange this a little bit to see if we can better understand what Ohm's law is telling us. I want to solve for current. So if I solve for current, let's see, we multiply both sides by I, right? Divide by R. So we get that current is equal to voltage over resistance. Okay, and here's where Ohm's law really starts making sense to us, right? So this resistor here, the current flowing through this resistor, how much electricity is actually flowing through the resistor depends on the voltage across it. If we have 1 volt across this resistor, and then we increase that to 2 volts, 10 volts, 20 volts, that will want to push along more current through that resistor. The more voltage we have, the more current is going to want to flow through that component. But it's inversely proportional to the resistance. It's in the denominator. So if we increase the resistance, 10 ohms, 20 ohms, 30 ohms, 50 ohms, by making the resistance more and more, you can see it quite literally lowers the current flowing through. So by increasing the voltage, we get more current. By increasing the resistance, making it harder to flow, we're going to decrease the current through the resistor. Okay. I have a little cartoon to show you. I really like this cartoon. I feel like it describes exactly what's going on here. So we have our current trying to flow through our circuit. The voltage is trying to push it along. Remember, the voltage source is our electrical pump trying to get that current to flow. And we have the resistance, ohm, there trying to resist that flow. Try to understand the story here. There's a lot of terminology, there's a lot of numbers floating around, but if you know what each quantity is trying to do to our circuit, you can better understand what's actually happening in our electrical devices. Okay. Next, I'm going to erase this. There we go. Before I go forward to some examples, trying to find some of the quantities of interest, I want to talk about a graph real quick. Let's say we're looking at that circuit that I drew before. And just like you guys did in the voltage, current, right? So we're looking at that resistor in our circuit, right? Let's say we start increasing the flow of electricity across that resistor. How does it affect the voltage? Well, for that resistor, we're going to need more voltage for more current to flow. These are directly proportional. So if we actually got data and we figured out how much voltage is across the resistor and how much current is flowing through the resistor, we're going to see a direct linear relationship. And not only that, but what if we calculated the slope? What would the slope of this line mean? Well, we know that R is equal to V over I. So change in Y over change in X, the slope here is equal to the resistance. Now I hear what you're thinking. Mr. Hatfield, why are we drawing graphs? What's the point here? Well, if we were to set up electrical devices, we can vary the current, we could vary the voltage, right? And we want to see how it affects our circuit. So for this resistor that we drew in the last example, we would get a direct linear relationship. We could calculate the slope, figure out the resistance of the resistor. Now, I have a little secret to tell you. Ohm's law, even though it's called Ohm's law, not a great name because Ohm's law doesn't always hold for all electrical devices. Ohm's law holds for devices like resistors. And when Ohm's law holds, we call this an ohmic conductor. We can use Ohm's law to analyze ohmic conductors. Resistors are always ohmic. But there are some devices that are non-ohmic, that don't obey Ohm's law. So what would a graph of an object that doesn't obey Ohm's law look like? If we vary the voltage, what does the current look like? If we vary the current, what does the voltage look like? Well, notice here that the slope is always the same at any point for this line, right? And if the slope doesn't change, then that means that the slope is constant and the slope is equal to the resistance. Well, for a non-ohmic conductor, if we got the same kind of data for that circuit, this graph wouldn't look so nice, so linear. We're getting this. So imagine you're in the lab, you vary the voltage, you measure the current. You vary the voltage, you measure the current. You vary the voltage, you measure the current. Here, for an ohmic conductor, you get a nice straight line. For a non-ohmic conductor, notice this is nonlinear. And the slope of this nonlinear line is never constant, right? The slope is always changing. This is what we call non-ohmic. So some devices are ohmic and they obey Ohm's law. Some devices are non-ohmic. They do not obey Ohm's law. So for an ohmic conductor, the resistance is constant because the slope is constant. For a non-ohmic conductor or non-ohmic device, resistance is not constant. So you'll have to recognize when something is non-ohmic, but for most of the devices that we're going to analyze, they are going to be ohmic, so you could use Ohm's law to figure it out. But real quick before I move on, notice how I said the resistance here is not constant. The slope of a volts versus current graph will tell you the resistance. Here the slope is constant, but here the slope starts out real small. It's low resistance down here. But then, as the graph goes, that resistance increases. So the resistance is not constant. All right, what do you say we try some examples? Got my little scroll thing, going backwards, here we go. All right, for all of these examples, they're gonna be ohmic devices, so we can use Ohm's law to analyze them. Here we want to find the resistance of a device through which a current of 0.5 amp, 0.5 amp flows when you have a potential difference of 9 volts placed across it. All right, I'm going to erase. All right. So let's say we have a mystery device again. We want to calculate the resistance. We know the voltage across it, and we know the current flowing through it. We have a current of 0.5 amp, 9 volts across it. So using Ohm's law, R is equal to V over I. Our goal is to find the resistance. Voltage is given, current is given. R is equal to the voltage given, potential difference is 9 volts. Current flowing through it is 0.5 amps. So how much resistance does this device have? How much is going to resist the flow of electricity? Well, we take 9 volts divided by a half. Dividing by something by a half doubles it, so the resistance here is equal to 18 ohms. Remember, use that upside down horseshoe to identify ohms. That's our unit here. Okay, and this is something that can be set up. If you have a 9 volt battery and you have an 18 ohm resistor and you hook up that type of circuit, you will get 0.5 amp of current flowing through it. To give you an idea too, resistors that are found in a laboratory, this is a relatively low value for this resistor. Resistors, like I said before, go up as high as kilo ohms, which is thousands of ohms, and mega ohms, which is millions of ohms. So we could always, we have any kind of resistor for whatever type of circuit we need. That's the resistance of that device. How much is going to resist the flow of electricity? All right, let's try another problem. All right, in this case, a device with a resistance of 150 ohms is connected to a 1.5 volt source. We want to find the current through that device. This 1.5 volts is telling us how much we're trying to push that current along. That potential difference is what we need for the current to flow. And we have 150 ohms, which is resisting that flow. With those two quantities, how much current is actually flowing in this circuit? Erase. Hey guys, when you get a chance, look around your house. Since you're on house arrest anyway, look around your house, look at some of the electrical devices in your house. If you look at any of the boxes that are on your laptop charger, right? If you look at any of, like sometimes like a little flag on the end of the wire, you can take a look at the wire and you can see the specifications that that device needs. For example, actually, I have a story for you. I was trying to figure out lighting for this whole studio setup here, and the plug I had wasn't working. I didn't know why it wasn't working. I plugged it in, the light was flickering, And then I looked and I saw that the plug that I had was delivering only 5 volts to the lamp, but the lamp needed, I think it was 13 to 24 volts in order for it to work. I wasn't providing enough voltage in order to work my device. So these electrical quantities play real role in our everyday lives. And by understanding what voltage is, what current is, what resistance is, you can easily troubleshoot things like that. If I didn't understand voltage, if I didn't know how to look at my electrical plugs, I wouldn't be able to have this beautiful lighting setup that I have here. Let's try this example. All right, a device with a resistance of 150 ohms, we went through that already. We're going to use Ohm's law. R is equal to V over I. Now you could plug in values here and get to your answer, or we could rearrange the equation and plug in later. I personally like to rearrange because our goal is to find the current. So if I solve for the current, you'll get I is equal to V over R. Feel free to play around with the equations we give you. This is all valid. This is still Ohm's law. This would also be Ohm's law. Right? All mathematically valid. So let's plug in now. The current flowing through this device depends on this 1.5 volt source and this 150 ohm resistor. This is trying to push the current along. This is stopping it. How much current is truly flowing? When you work it out, you will get, always work this out before I give you the answer, 0.01 amps. Okay. This is 10 milliamps is flowing through this circuit. And this is pretty standard for any kind of household, tabletop electronics that you have. You can actually order electronics kits online. And they'll send you all these little resistors and wires, and you can start building these circuits on your own. If you build a circuit with a 1.5 volt source, which is usually the voltage of like a watch battery, I believe. A 1.5, oh no, full 1.5 volts is AA, AAA, AA, AAA, sorry. AA, AAA, CD is all 1.5 volts, and you put a 150 ohm resistor in that circuit, you will get 10 milliamps of current flowing through that circuit. All right, let's try another example. Okay, the last thing I would like to discuss for today. So before we were kind of discussing these graphs of voltage versus current. And here a voltage versus current graph is given to you. We have some device, and we got some data points. And we plotted these data points, and we see this linear best fit line. First ask yourself, is this object, is this device ohmic or non-ohmic? Does it obey Ohm's law? It does obey Ohm's law because the slope here is constant. Yes, we have some points that are floating above and below the line, but we could chalk that up to experimental uncertainty. You can see that in general, this is a linear relationship. Now, if I had points that were like all around here, then I would say a better fit would be a non-ohmic or a non-linear line here. Non-linear line. Non-linear curve. Okay. So, our goal here, we want to calculate the resistance of this device based on the information that is given. We have this graph. How do we possibly find the resistance when a graph like this is given? I'm going to erase. Okay. Well, if you recall, when we have a graph like this, voltage versus current, the slope is equal to the resistance. So if we find the slope of this line, we will know the resistance of this device. Before we dive in and solve, I want to tell you to always check your axes very, very carefully. You need voltage on the y and current on the x in order for the slope to be the resistance. What if those axes were flipped? What if I had current on the y and voltage on the x? Well, in that case, the slope of that line wouldn't be the resistance, it would be 1 over the resistance. It would be the inverse of the resistance, right? Because we're flipping our equation around. But because voltage is on the y, current is on the x, we know the slope is going to be equal to the resistance. You don't have to memorize that, you just look at Ohm's law. V over I. Right? Slope is change in y over change in x. It's already set up that way. So we got our resistance. So let's figure it out. Change in y over change in x. Well, if we look, we can see these endpoints fall right on the line. I know I always tell you in class you want to pick points on your trend line, but because these points fall perfectly on the line, I'm going to say it's okay to use these endpoints here. But you can pick any point you want, and you should still be able to get to the resistance. As long as they're on the trend line, you can't use data points if they're off the trend line. Okay. So change in y, let's go through those two endpoints. We have 20 volts subtracted by 0 volts, right? y2 minus y1 over x2 minus x1. x2, the current here, so I went voltage here, current is 0.8 amps. That's 800 milliamps. Okay. And when we work this out, 20 volts divided by 0.8 amps, we're going to get a resistance of 25 ohms. Okay. And the very last question I'm going to ask you for this video. Let's say I hooked up another device that has a lower resistance than this device that we analyzed here. A lower resistance, what would that data set look like? What would the graph look like? Well, here's the graph that we have for our current device. What would the slope look like if the resistance were less? What would the graph look like? Well, if we have a lower resistance, we need to have a lower slope. But if it's still an ohmic element, it still has to be a linear relationship. So this dotted line would be the example of a device with less resistance than the device given up on the board. Okay, and that is it for now. We're not done using Ohm's law. This is just an introduction to Ohm's law. We're going to be using Ohm's law in the future to analyze more complex circuits when we start throwing more devices inside of our circuit. And we're going to keep referring back to this law to analyze these types of circuits. I hope everyone's doing well. Feel free to reach out anytime if you guys need physics help or you just want to chat. I'm always around for you guys. I hope everyone's doing well, hope everyone's staying safe, and I'll see you in the next video.